This is the lesson on solving inequalities by multiplication and division. Unlike the case with addition and subtraction, if you have something like a times x is less than b, you can't just divide both sides by a. At least, not always. The same goes for multiplication. There is a very special exception when using multiplication and division with inequalities. Let's start by example. If a variable q was greater than 2, we could draw this on the number line at a point 2. Q is going to be always greater than, not equal to, 2. What if, after you did this problem, I told you that secretly it turns out q is actually negative x? That means that negative x is greater than 2. But if q is negative x, and we compare both of these graphs, we might find that x would have to be negative values of q. That means that where I originally cared about 2, now I care about negative 2. And if q were to be, let's say, 3, x would be negative 3. So x can be any number before negative 2, except for negative 2. So now we know that this represents the relationship I'm talking about. But if we were to look at this, you might first approach it by saying, okay, multiply both sides by negative 1, and you get x is greater than negative 2. But that's clearly not the case, because that would look like the same thing, but on the other side. And this is where the exception comes in, and it deals with any negatives. If we forget about what I've written down below, and we look up here again, we can see that for this relationship, on top I'm talking about q, on the bottom I'm talking about x. Where q was 2, it kind of was like when x was negative 2. In truth, q could not be 2 because it's always greater than 2. But let's look at this again. If q is 3, x would be negative 3. If q was 4, x would be negative 4. Everything is reflected on the other side. Because it's reflected, we can say if we have negative x is greater than 2, we've got to reflect it when it's negative. So I multiply both sides by negative 1, and I take the reflection. So where we had greater than, we now have less than. Similarly, if I had q was greater than 2, and then I told you that q was actually 2x, you could say that 2x was greater than 2. Now ask ourselves, does that mean x is greater than 1? Well, let's check. So I've drawn the relationship for q above, that q is greater than 2. Now if q is just 2x, that really means when q is 2, even though it's not actually 2, x would have to be like 1, even though it couldn't actually be 1. So here I have a point at 1, and that's associated with when q is 2. So now let's say q is 4. When q is 4, x would have to be 2. So this means that we know this is on this line. So this is what the line looks like. So in that case, x indeed is greater than 1. What this tells us is that multiplication and division only gets iffy if you ever have to multiply or divide by negative 1. And whenever this happens, you have to flip the sign. So if you started off with less than, you would end up with greater than. If you started off with greater than, you would end up with less than. Less than or equal to becomes greater than or equal to. Greater than or equal to becomes less than or equal to. Essentially, if you ever have to multiply or divide by some negative number, You can take whatever sign you start off with, look halfway through, and just reflect it. And you'll get what it becomes. But in the case where you don't have a negative number, it's just some positive a, then you can just finish with whatever you started off with. The examples should help clarify any questions you may have about this property.